You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we begin in a room that doesn't look like destiny. No thunder, no towering machine, no dramatic apparatus. Just paper, a desk, and a man who is quietly trying to do something most people don't realize is possible. He is trying to write down the laws of light. Outside, the 19th century is a century of iron and smoke. Telegraph lines stitch cities together with copper nerves. Electric sparks jump between metal spheres in lecture halls. Magnets tug needles into order. The world feels newly alive with forces that cannot be seen but can be made to obey. Yet these forces, electricity and magnetism, are still in a deep sense separate stories. A magnet pulls, a charge repels, a current warms a wire, a spark snaps the air. The scientists of the time can measure effects, build devices, and write partial rules. But no one has yet produced the single language that makes those rules feel like one phenomenon viewed from different angles. No one has yet turned the strange, beautiful empirical craft of Michael Faraday into something that can travel in ink. And then there is James Clerk Maxwell. If you want the myth, you can imagine him as a wizard, a man who looked at the world and saw hidden equations floating in the air. But if you want the truth, the kind of truth that matters as you're trying to understand how science actually moves, you have to begin in a quieter place. Maxwell's genius was not only brilliance, it was translation. He took an intuitive, visual, almost poetic way of thinking and turned it into mathematics that would outlive its maker. He did something rare. He honored another mind by giving it a more permanent form without stealing its soul. Maxwell was born in 1831 in Edinburgh, Scotland, into a world where education and religion were woven into daily life, where a serious boy could still be left alone with fields, tools, and questions. His family was comfortable, not aristocratic in the grand sense, but well-positioned enough to give him books, time, and access to schooling. His mother Frances died when he was 8. That early loss left a mark that never fully healed, and his father John poured himself into raising him, protecting him from ridicule when he was young and odd, and encouraging his curiosity even when it arrived in strange forms. Maxwell was the kind of child who didn't just ask what something was called, he asked what it was. When he looked at a piece of string or a curve, he wanted to know how it behaved, how to describe it, how to make it repeat. At school, he was teased for being rustic, for his accent, for his homemade clothes. But he had an ability that turned teasing into background noise. He could go inside a problem and live there. By his teens, he was producing original work. One of his early papers, written when he was just 14, described the geometry of oval curves, how to generate and classify them. It was the kind of work that doesn't make a young person famous, because geometry is not flashy, but it's a clue to the mind. Maxwell loved structure. He loved hidden simplicity. He loved the idea that behind a messy surface, there might be a clean rule. He went to the University of Edinburgh and later to Cambridge, where he thrived. Cambridge was an engine for mathematical talent, and Maxwell was one of its finest products. But he wasn't simply a calculator. He was a builder of models. He thought in images and analogies and then tested them with mathematics until they either broke or held. That combination, imaginative modeling plus ruthless mathematical discipline, would become his signature. Before electricity and magnetism fully claimed him, Maxwell did significant work on color vision. He studied how the eye perceives color and developed ideas that would later underpin color photography. In 1861, he demonstrated one of the first color photographs by taking 3 images through different colored filters and projecting them together. It is tempting to treat that as a charming side project, but it's more than that. It shows something central. Maxwell believed that invisible processes could be made visible with the right apparatus and the right theory. He trusted that sensation and measurement could be bridged. He also worked on the kinetic theory of gases, describing how gas particles move and how their speeds distribute in a predictable pattern, the Maxwell distribution. Again, there is a pattern. Maxwell liked taking a chaotic crowd, molecules, colors, fields, and discovering the statistical or mathematical order within it. Then came the great translation task. In the middle of the century, Michael Faraday was the most extraordinary experimentalist in Britain. Faraday was born poor, with little formal education, and rose through the world of lectures and laboratories on a wave of talent so undeniable it forced institutions to make room for him. But Faraday's mind did not live in mathematics. It lived in pictures. When he investigated electricity and magnetism, he did not talk primarily about forces at a distance, acting instantaneously across empty space. He talked about lines of force. He imagined fields filling space, like tension in a medium, like invisible threads that could be bent and stretched. He would sprinkle iron filings around a magnet and watch them arrange themselves into arcs, and he saw, in that pattern, not a mere convenience, but a physical reality. Many mathematicians dismissed Faraday's language as vague or metaphorical. They respected his results but not his style. Faraday, in turn, was wary of mathematics when it pretended to be more real than the phenomenon itself. He wanted physical meaning, not elegant symbols. Maxwell saw something else. He saw that Faraday's lines of force were not a poetic crutch. They were the embryo of a deeper theory. Faraday had discovered, through experiments, that changing magnetic fields can induce electric currents. He had shown that electricity and magnetism were coupled in time. He had cracked open the idea that these forces are not separate at all, but aspects of one phenomenon. Yet Faraday's discoveries were scattered across experiments and descriptions, like a map without a legend. Maxwell decided to write the legend. He began by building mechanical analogies. This is one of the strangest and most important parts of the story because it shows how scientific creativity works. Maxwell did not begin by declaring, "Here are the equations." He began by imagining space filled with tiny vortices and idle wheels, mechanical components that could represent the behavior of fields. He used this machinery not because he believed the world was literally made of spinning ether vortices, but because the mechanical model let him translate Faraday's intuitions into mathematics. The model was scaffolding. Once the building stood, the scaffolding could be removed. In 1864, Maxwell presented a paper with a title that sounds modest: A Dynamical Theory of the Electromagnetic Field. It contained a revolution disguised as careful reasoning. He gathered the known laws of electricity and magnetism, Coulomb's law, Ampere's law, Faraday's induction, and sought consistency. He asked, if a changing magnetic field can produce an electric field, can a changing electric field produce a magnetic field? The symmetry of the question is almost too neat, but nature is sometimes neat when you look at it the right way. Here is where Maxwell performed the move that would reshape physics. He realized that Ampere's law, as it was then understood, was incomplete. Ampere's law related magnetic fields to electric currents. But consider a capacitor, two plates separated by a gap, charging as current flows. In the wire leading to the capacitor, there is a current. In the gap between the plates, there is no conduction current, no charges crossing the space. Yet a magnetic field exists around the circuit as the capacitor charges. If you apply Ampere's law naively, you get a contradiction, depending on how you choose the surface over which you compute the current. The mathematics would not be stable. The universe seemed to be cheating. Maxwell refused to accept a law that depended on how you drew your surface. He introduced a new term, the displacement current. It wasn't a current of charges moving through space, but a term representing the changing electric field in the gap. A changing electric field, he proposed, acts like a current in producing a magnetic field. With that addition, the equations became consistent. This is one of the moments when you can see the difference between a clever scientist and a world-changing one. Maxwell did not merely patch a leak. He recognized that the patch was a new pipe connecting two systems. He saw that the changing electric field was not a minor detail. It was the missing piece that made the whole structure coherent. Once you accept the displacement current, the consequences unfold almost with inevitability. If changing magnetic fields create electric fields, and changing electric fields create magnetic fields, then the two can sustain each other. A disturbance in the electromagnetic field can propagate through space as a self-sustaining wave. Electricity and magnetism can dance forward together, each generating the other as they move. Maxwell did the mathematics and found the speed of these waves. When he computed it using known electrical and magnetic constants, the number that emerged matched the known speed of light. Not approximately, not vaguely, but strikingly. The conclusion was as simple as it was shocking: light is an electromagnetic wave. This is the moment the episode's title points to, when light became an equation. Not because Maxwell reduced beauty to symbols, but because he revealed that the beauty was lawful. Light, This ancient mystery, this thing poets used as metaphor and philosophers used as proof, was now understood as a ripple in a field. It was not a separate essence. It was electricity and magnetism moving in lockstep through space. If you are listening from the modern world, where electromagnetic spectrum is a phrase that appears on diagrams in middle school textbooks, it is hard to feel how radical that was. Maxwell unified phenomena that had been treated as distinct: static electricity, currents, magnets, optics. He built a single framework that could explain them all. He gave the 19th century something it was hungry for: a deep unity. And he did it in a way that suggested there might be other waves beyond visible light, other frequencies the eye could not see. That implication would soon become reality with the discovery of radio waves and the birth of modern communication. When we say Maxwell laid the rails for Einstein, we mean something precise. Einstein's special relativity is built on the fact that the speed of light appears as a constant in Maxwell's equations. The equations were telling the world something about space and time, and Einstein listened. But Maxwell himself lived in the transition period where the old idea of an ether, a medium filling space through which waves propagate, still felt necessary. Sound needs air, water waves need water. If light is a wave, 19th century physics reasoned, then it must wave through something. The ether was hypothesized as that something, an invisible, all-pervading substance with odd properties, massless but stiff, undetectable but real. Maxwell did not kill the ether. In some ways, he strengthened its perceived necessity by treating fields as physical entities in a medium. Yet his equations did not truly require the ether as a mechanical substance. They required only that fields exist and that their changes propagate. That shift, from forces acting instantaneously at a distance to fields existing throughout space, was a profound philosophical change. It meant empty space was not empty. It had structure. It could store energy. It could be stressed. It could carry waves. The field became a new kind of reality in physics, not merely a mathematical convenience. Maxwell's own life was not built for public drama. He was intensely private, deeply religious in a way that was thoughtful rather than performative, and often playful in his personal writing. He married Catherine Mary Dewar in 1858, and their marriage appears, from letters, to have been close and intellectually supportive. They had no children. His career took him to Aberdeen and London, and eventually to Cambridge, where he became the first Cavendish Professor of Physics. He helped establish the Cavendish Laboratory as a place where precise measurement and theory could feed each other, where physics could become an institutional engine rather than the work of lone geniuses. He also wrote a monumental treatise on electricity and magnetism, published in 1873, which formalized and expanded his theory. The treatise was not easy reading. It was dense, careful, filled with reasoning that expects the reader to work. Yet it became a foundational text. It trained a generation of physicists to think in terms of fields and equations, not just instruments and sparks. Maxwell's equations, as we write them now, are often presented as four elegant statements: Gauss's law for electricity, Gauss's law for magnetism, Faraday's law of induction, and the Ampere-Maxwell law including displacement current. In Maxwell's original form, they were more numerous and less compact, expressed with components and potentials. Later mathematicians, using vector calculus, compressed them into the Clerk set we now celebrate. But the heart of the achievement is Maxwell's: the conceptual unity, the insistence on consistency, and the leap to electromagnetic waves. What is easy to forget is that Maxwell's contemporaries did not immediately embrace his vision. Some experimentalists found the theory too abstract. Some insisted on mechanical models of the ether and were uneasy with fields as primitives. It took time and proof. That proof arrived after Maxwell's death, when Heinrich Hertz in the late 1880s produced electromagnetic waves in the laboratory, radio waves, and showed they behaved exactly as Maxwell predicted. Suddenly, the equations were not just elegant, they were true in the most satisfying way. They pointed to phenomena no one had yet seen, and then those phenomena were found. Maxwell did not live to see Hertz confirm his waves. He died in 1879, at the age of 48, likely from abdominal cancer. The tragedy is not only that he died young, it's that he died just before the modern world he helped create began to bloom. Yet his influence is everywhere. Every radio signal, every wireless transmission, every antenna, every microwave oven, every MRI machine, every optical fiber carries the signature of Maxwell's unification. Even the language of fields that now pervades physics, gravitational fields, quantum fields, owes a debt to the way Maxwell made fields feel real. And then there's Einstein. Einstein, as a young man, read Maxwell's theory and felt its pull. Maxwell's equations predict a constant speed of electromagnetic waves in vacuum, independent of the motion of the source. But classical mechanics, with its intuitive addition of velocities, could not accommodate that. If you run toward a beam of light, classical thinking says you should measure it as slower relative to you. Maxwell's theory says no, the speed is the same. That tension haunted physics, until Einstein resolved it by changing the structure of space and time, not the equations. In that sense, Maxwell's work was not merely about electricity and magnetism. It was a doorway into a new universe. If you want an image to carry away, don't picture Maxwell as a thunderbolt genius shouting formulas into the air. Picture him as a translator at a desk, taking Faraday's lines of force, those invisible arcs traced by iron filings, and finding a way to write them so the world would finally understand what Faraday had been seeing all along. Picture him checking consistency, refusing contradictions, adding a term not because it was fashionable, but because the universe demanded it. Then picture the moment he realizes that the speed emerging from his equations is the speed of light. That moment is the quiet hinge on which the modern world turns. When light became an equation, it did not become less mysterious. In some ways, it became more so. An equation can predict where the wave goes, how it bends, how it reflects, how it propagates. But the equation also reveals that light is not merely illumination. It is a manifestation of deeper structure, of fields in space that can move and carry energy and momentum without any visible substance. Maxwell gave us the first great unification of modern physics, and he did it with humility and rigor, with a style that was more patient than flashy. You have been listening to Scientific Giants Who Changed the World. Today we followed James Clerk Maxwell as he turned Faraday's visions into mathematics, unified electricity, magnetism, and light, and wrote down laws that would guide physics into the 20th century. In our next episode, we will meet a man who did not want to be a revolutionary, but became one anyway. Max Planck, who tried to fix a stubborn problem in black-body radiation and ended up quantizing energy, cracking classical physics, and opening the door to the quantum world. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because ideas land differently when they arrive like a narrative instead of a list. Until our next hour together, remember this. Sometimes the greatest revolutions are not announced with trumpets. Sometimes they arrive as a small correction in an equation that suddenly makes the universe make sense.